All right, in lesson 94, we're going to graph pairs of inequalities on a number line. Sometimes instead of pairs of inequalities, people might call these compound inequalities. That's what I've always called them in the past. So we're going to graph compound inequalities on a number line today. And here's what I mean by compound inequalities. When we've got something like this, where -3 is less than x and x is also less than 3. Some people might just say that x is between -3 and 3 when they look at something like this. Okay, so let's graph this. First of all, let's scale our number line. And since x is between -3 and 3, we'll do open dots on -3 and 3. And then we'll just draw a line between them. There's all the values of x that would solve this inequality. So all values that are greater than -3 and less than +3 without being -3 and +3. Remember, we use open dots when there's no line under the inequality, just like here. So nothing's changed here. Now in example B, it's a little bit different because it says x is less than or equal to -3 or x is greater than or equal to 3. Show you what this looks like. First of all, let's scale our number line. Scale it the same. It says x is less than or equal to -3. Now, or equal to, that means it's a closed dot. Less than would be an arrow to the left. And or x is greater than or equal to 3. So that would be a closed dot because it's or equal to. And greater than means an arrow to the right. So this kind of sums up everything we're looking at here. Open dots when it's less than, greater than would also be an open dot. Closed dot when you're talking about less than or equal to, or when you're talking about greater than or equal to. Now in and situations, it'll look like this when you write the inequality, and it'll always be kind of the two dots being joined together by a line segment. Or segments, or inequalities like this, you're always going to have arrows going away from each other. You have to say the word or because there's no number that is less than or equal to -3 and greater than or equal to +3. Let's do this a couple more times. 5 is less than x, which is less than or equal to 10. So another way to say this would be that x is between 5 and 10, including 10, because it's or equal to. So let's scale this. I'm going to start at 4 and go up to 10. I'm going to put an open dot at 5, and I'm going to put a closed dot at 10 because it's or equal to 10, and then I'm going to join those two. And that's it. I've graphed this compound inequality. This shows all the numbers that are greater than 5 and less than or equal to 10. So all these numbers in between satisfy both those requirements of being greater than 5 and less than or equal to 10. Now in example D, it says x is less than 0 or x is greater than or equal to 5. So let's graph all the numbers that fit those two criteria. So let's scale our number line. Start at 0. I'll go up to 6. Less than 0 be a closed dot at 0 with an arrow to the left. And greater than or equal to 5 would be a closed dot at 5 and an arrow to the right. So this graph shows all the numbers that are less than 0 or greater than or equal to 5. And last one. A college will cancel a lab class if less than 12 students enroll. So yeah, if they don't have at least 12 students, they're going to cancel the lab class. No more than 30 students can enroll in one lab class, so they don't want to have too many students in the class and the teacher can't get around and help them all. So write an inequality that shows the number of students, S, that could be in a lab class and illustrate this inequality on a number line. Okay, so first of all, let's write our inequality and then we'll graph it. So it's got to basically be between 12 and 30. That's the easiest way to state it. So we say it's greater than or equal to 12, less than or equal to 30. And x is also a whole number. This throws a little bit of a kink in our thinking here, but I'm gonna put that caveat on there that x has to be a whole number because you can't have a half of a student. So we're gonna say it's got to be a whole number. So that's going to change the way our graph looks here a little bit too. Let's start off by scaling it. I'll go by fives, starting at 10 and going up to 40. I'm going to put some markers in between here for 11, 12, 13, and 14. So 4 equally spaced markers in between each one. And then I'm going to plot these points here. So between 12 and 30, including 12 and 30. And since it's got to be a whole number, we can't just use a line that connects the 12 to the 30. So we have to actually plot every single one of these. So here's the possible students that could be in this lab class. It's greater than or equal to 12, less than or equal to 30, and only whole numbers. It's a little bit goofy, but hopefully you kind of get the idea. We don't want to show that 24.5 is a solution or that 21.2 is a solution because you can't have 21.2 of a student. That's the idea of using the dots instead of the lines. Takes a little bit longer, but it kind of makes sense. That's all I've got for today. Rewatch if necessary. If not, I'll see you tomorrow.